Hello, guys. Welcome to day three of my stream. Well, we have to continue. But I must tell, it's raining outside, and there's a high chance of two things. Okay. First thing is my electricity can fall out anytime. And second thing is that my Wi-Fi can betray me anytime. So still I'm streaming because I really wanted to stream at night, but I couldn't due to some stupidity. But I guess it's fine. I can stream right now. Let's see what happens. Oh, I'm not late. Okay, I'm not late. I'm 1 minute early. Hello, hello everyone. Thank you for joining. Real Tushar. Thank you for joining. So before I continue today's lesson, okay. Um, I should actually review previous classes. I should not say classes. Class word just messes me up. Okay. I should say this. What should I say this? Walkthrough sessions. Okay. I should revise my previous walkthrough sessions. Okay, that sounds cool to me. Fine. Um, I think I place my books here. Okay, what did we study at day one? Some really cool shit. So it's just if I have to review very quickly, we know that theory of computation deals with three central areas that are automata, computability, and complexity. If I say about complexity theory basically classifies a problem as easy or hard based on the computational difficulty. And we kind of maintain a table of a database of very hard problems that are proven hard problems. And if any problem we are facing um, can subset that hard problem, that means that this problem is also hard. And that's how we prove if a problem is easy or hard. That's how we classify a problem is easy or hard. And that is what we study in complexity theory. And there are many ways to approach these hard problems, how to actually solve them, how to make algorithms, how to design algorithms to solve them. We can actually alter the easier part of problem. See, a problem is hard not because it is completely hard. Some parts of that problem are hard. Sub problems. If you can actually divide a problem into many problems, and then um, whichever part is the hardest, you can alter it and change the problem statement in such a way that it gets kind of easier, and then it is solvable. If this is not the case, then maybe we can approximate the problem. And if approximation is also not possible, then maybe we can solve in other cases than worst case. Because you see, the worst case scenario is always hard for most of the problems. But if we just ignore the worst case, rest is just rest just easily false. Then next is computability theory. All right. So computability theory classifies both of them classify. Complexity theory classifies problems as easy or hard, and computability so classifies problems as solvable and non-solvable. So that's just easy to understand, I guess. Then finally, automata theory. Automata theory is basically a set of rule books, I think. It defines and gives us properties of various mathematical models of computation. We study finite automaton here, context free grammar, and basically all the rules that will eventually help us to study complexity theory and computability theory. Fine. So after we uh, after we read all these things about TOC, very basic stuffs, the book actually introduced us to basic mathematics. And in basic mathematics, we saw sets, relations, and functions. Every basic mathematics starts with those three chapters. And I have not written all of the definitions I found here, because the stuff, that particular stuff, I've already read the stuff in my high school time, and some part which I felt is um, not in my memory, I just wrote it. Well, you might think this is so dumb stuff to write, but let's just ignore this statement. A sequence with k elements is a k tuple. That might be something I might not remember 2 days from now. A two tuple is called ordered pair. Then some notations to represent functions, and then you see, this is something na, I might confuse in syntax. My mathematics is not that good for now, but I'm progressing daily, slowly. So you see, these domains, I have written a set here, but this set can also be a tuple, right? Just like I wrote, a sequence with k elements is a k tuple. A function can take a set of arguments, and a set of arguments can be represented as a tuple, right? You just supply an input tuple to a function to get an output. So that tuple will be defined with a relation, and thus I can specify that I can just let the domain of function f be uh, cross product, a set of cross products, and which just means that function is a k tuple. Okay, input of function is a k tuple, the domain of function is a k tuple, and there are just some definitions I have written here, that if a function with k arguments is called a function with k arguments is called k array tuple, and k is the arity of the function. If k is 1, then it is unary function, and if k is 2, then it is binary function. And to write actually binary functions, we can represent binary functions with infix notation and prefix notation. In infix notation, we just write the operator between the operands, and in prefix notation we kind of write the operator on the prefix side. Okay, just like I symbolize the add keyword and have written the add symbol keyword before uh, before the tuple of what do you say, operands. All right. Then there is another statement, a predicate. What is predicate? Predicate is just a property. Property is a function whose range is true or false. Okay. For example, even property. That is just easy to understand now. And finally, equivalence relation. Any relation which is reflexive, symmetric, and transitive. Um, I think I don't need to specify what are reflexive, symmetric, and transitive relations. You can just Google it at this point. Then diving to day two of my notes. All right. So in day two, the book introduced us to graphs. Okay, and graphs. I have read graphs, studied graphs, but very little. Okay, so I kind of needed to write very basic stuff here. So graph is a set of points with lines connecting some of the points. Okay, fine, easy to understand. The points or nodes are called vertices. The lines are called edges. Then I just represent a graph. The number of edges at a given node is called degree of that node, and these are some what do you say, alphabets to represent some sets. And what are those sets? Just say V is a set of nodes, G is graph, and E is a set of edges. And to represent a graph, you need a tuple, and in that tuple, you just write these two sets as it is. Okay, first set is set of vertices V, and second set is set of edges. Fine. I should actually write also in chat. Okay, the bigger graph. Okay, where was I? Ha. If you have a graph, you can extract a subgraph from it, and that's just okay, fine. Um, what's the path? Let's say you start from a point, and you have to keep progressing from that point without looking back. and that's a path. Okay, that's cool to listen. What do I mean by don't look back is that you can't repeat a node which you have already covered. For example, here I let's say I am at 1, then I move to 4, then I move to 3, and then I move to 5. Now I can't move back to 3. If I do so, then it's not a path. Okay, actually that's a path, but that is not a simple path as per the definition. A simple path is a path that does not repeat any nodes. Okay, I remember that, guys. I remember that. A graph is connected if every two nodes have path between them. A path is a cycle if it starts and ends in the same node. A simple cycle is the one that contains at least three nodes and repeats only first and last node. Fine. Now we are introduced to directed graphs, which have directions, of course, and we see that if you have to define degree of the graph, the degree of this vertex side here is 3, because we see 3 edges uh, joining it, okay, or leaving it, but we don't know joining or leaving, so we just define 3 total value. Okay, but here we actually can define what is leaving and what is coming, right? For example, 1, there are 2 edges leaving from it, and these type of edges are called out degree. Okay, pointing from a particular node is called out degree, and number of arrows pointing to a particular node is called in degree. Okay, that's very good wordplay if you can understand just by seeing the word. Finally, we compare a binary relation with directed graphs. And actually, in previous stream, I spent a lot of time studying binary relation because the word binary was kind of confusing me. But that's very simple. This is literally saying you just write A cross B, and this is a binary relation. Because why this is binary? Because we have two operands, and that's why it is binary, and that's it. This is no confusion. Just a kind of wordplay which might scare you. It actually scared me, but I'm fine with it now. So we compare binary relations with directed graphs, and how we compare them? If we have an element x, okay, we can compare that to vertex x. For example, in this binary relation, let's say we have two sets A and B. Fine. And in these two sets, we can actually write these two sets like what? Like what? We can write these two sets like it has elements A, B, C. Fine. And we can write B set as, let's say, D, E, F. Okay. Now we say this element x, and this element x is comparable to vertex x. Um, let's just define A like this, B like this, and C like this. Then D, E, and F. We can, according to this relation, let's say this relation is like this. We connect A to E, we connect C to D, and we connect B to F. This is the relation. And what is this? This is a graph, right? We are just connecting some vertex with lines, with edges. So this is a graph, and this relation xy, x to y, that is A to E. This is a relation. Like, this is a relation, and this pair is actually represented by um directed graph, right? I can specify an arrow between them, and that's it. I can compare this precisely to this. Relation R is just edge. This edge represents relation, of course. And as R is the subset of D cross D, like A cross B, G is just set of D and E, where D is domain. Domain is what? Domain is just this A cross B again. And E is the set of edges. And we see the edges uh, by the what was the term? Two tuple. Okay, we represent edges with two tuples. Like we can say AE, this is a two tuple. We can say BF, this is a two tuple, and so on. Fine. Uh, then we were introduced to alphabets. I should erase this. No, this is not really necessary for notes. Maybe I should keep this because maybe for next revision session this might actually help. Okay, save. Then we were introduced to alphabet and those TOC stuffs again by the book. And what is an alphabet? With our English vocabulary, we understand alphabet as just like an alphabet, capital A or small a. No, what was the term? It's not small a. Rhythm Goyal. Hello, Rhythm. You are in class. Okay. Thanks for joining during the class. It's really painful to join class, I know. That's why I don't call this a class. Thanks a lot. Okay, so alphabet is just capital or non-capital letters of English or any language, but in mathematics or theory of computation, I say an alphabet is a non-empty finite set. So what is an alphabet? Alphabet is a set, and to represent sets, we use capital letters again, but not here. Here to represent alphabets, we just use the sigma notation, kind of this, and we can just write any set. Okay, and that set can contain any symbol. Okay, and those symbols are again called alphabets. But to not confuse you, we should actually disperse the terms. We should call alphabet as a set, and whatever elements are present in those set, we will just call them symbols. Okay, so what's a string now? A string over an alphabet set is a finite sequence of symbols again from that alphabet. So I use the word symbols, but I think the book actually used the word alphabets again, so that's fine, understandable. And there is something called short lex order. And what short lex order is, same as normal lexicographic dictionary order, with just one minor difference, that shorter strings will always precede the longer strings. All right, now what about actually, now we were introduced to some discrete mathematics operations. Okay, and I just wrote those things which I think people generally forget. I generally forget. XOR operation. XOR operation is just OR operation with just one difference. Then that when all the signals are high pulse, okay, then it will actually output low signal. Okay, if all the values are one, then output will be zero. Then there is one called equality operation, and it is if equality operation is one if both operands are same. Okay, so I mean, I should actually see it as, does equality operation take only two operands? Because because typically all the discrete mathematical operations are written as if they can take only two operands, but actually if we study them deeply, we find out that they can take as many arguments as they can. Okay, for example, if I just talk about AND operation, very simple, one 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 one, but single zero. If I take AND between all of them, even you can just tell that answer is going to be zero just by saying this last number. And why is that? Because your brain just took all operands at once. You just kind of uh, did the AND operation for all the operands. But maybe I can see it like A, B, C, and do them maybe like this. Now this operation, let's say, yields 1 or 0. Let's represent 1 or 0 as Z maybe. Then ZC, and maybe we can chain it like this. And that's how these operands are termed as binary. So, okay, if both operands are same, I should highlight operands are same this. If both operands are same, then our answer will be 1. Then implication operation, it's the forward arrow, and this I remember, if A then B. Okay, so if 0 is the first operand and 1 is the second operand, answer is 0, and all the rest of the cases which are left, answer is always 1. This is the only exception case we need to remember for implication operation. Then we see some identities. Okay, to actually convert these equality and implication operation with basic and or not operation. Okay, and or not gates. So that's it. We have implication, and implication is equal to not P or Q. This is equality operation, and equality operation is just P then Q, Q then P, and between those operations. And again, you can represent then thing with this. So I can write this as not P or Q, not Q or P. Okay, and there is and between them. So basically, the point is that we can write everything, every single gate, um, as and or not gates. Okay, that's the idea. So that's a great idea. And now we finally dive into definitions, proofs, theorems, lemmas, corollaries, things like that. I was actually always confused with these terms. What is a lemma? What is a corollary? And what precisely is a theorem? Yeah, I know proofs. I have done proofs, some proofs. Definitions are also understandable, but yeah, matlab, what is a theorem? Matlab, if I give you a statement, how can you classify it as theorem or lemma or corollary? How do you know if it is something from these three words? So that's something I don't know. So this is the thing we have to explore in today's session. So yeah, definitions, theorems, and proofs. Theorems and proofs are the heart and soul of mathematics, and definitions are its spirit. These three entities are central to every mathematical subject, including ours. So, what is a definition? Definitions describe the objects and notions that we use. Sorry for the wrong pronunciation. Definitions describe the objects and notions that we use. A definition may be as simple as, like, definition is a set, definition of set given earlier in this chapter, fine, or as complex as the definition of security in cryptographic system. Okay, uh, precision is essential to any mathematical definition. While defining some object, we must make clear what constitutes that object and what does not. What do you mean by this line? What constitutes that object and what does not? Let's see. After we have defined various objects and notions, okay, so basically we need to define every single term that we are going to use, and then we need to define whatever term we are going to define now. We usually make mathematical statements about them. Okay, so basically I think it is trying to say that we first make mathematical statements, and then we, let's say, we prove those statements, we make theorems of those statements, maybe lemmas, corollaries, things like that, and we then use those things to define a term that comes along our way. Typically a statement expresses that some object has a certain property. Okay, fine, understandable. That statement may or may not be true. Fine, but like a definition, it must be precise. Uh, okay, no ambiguity about its meaning is allowed. We just talked about precision a while ago. So, precision in mathematics is very important. A proof is a convincing logical argument that a statement is true. So, it's all about precision and statements, like defining if statements is true or not, mathematical reasoning. In mathematics, an argument must be airtight, that is convincing in an absolute sense. In everyday life or in the law, the standard of proof is lower. A murder trial demands proof beyond any reasonable doubt. The weight of evidence may compel the jury to accept the innocence or guilt of the suspect. However, evidence plays no role in mathematical proof. A mathematician demands proof beyond any doubt. Okay, so after we prove statements, we classify them. Okay, so uh if I'm if I understand it correct, there is a statement, there is some mathematical statement, and we then define this statement. We then prove this statement as true or false. So this statement can be true. I just hate it when this takes this shape, because this shape has literally no use. Why this mouse shape is becoming to resize? There's nothing to resize there. I don't know, maybe it's because of the split. Okay. A statement can be true. Ah, man, this is really annoying to me. A statement can be true, a statement can be false. If the statement is true, okay, then we basically say that it's a theorem. A theorem is a mathematical statement proven true. Generally, we reserve the use of that word for statements of special interest. Occasionally, we prove statements that are interesting only because they assist in the proof of another statement. Okay, more significant statement, another more significant statement, fine. And such statements are called lemmas. So, not every proven true statement is called theorem. For some, we call them lemmas. And what are those sum statements? Those sum statements are basically those which help to prove another statements. So I think if I get this right, okay, if I get this right, you use statements for two main purposes for now. Okay, what I've seen, there is statement, and we use this. I mean, proven one, right? True statement. We use this to define terms and also to like prove another statement. And if I get this right, If you are using it to define something, then it is called a theorem. And let's say if you are using it to prove another statement, then it is called a lemma. Am I right? Hello, chat. Am I right? I think I think I might be I may be really wrong here. Okay. Let's just continue for some time and then we will search this. Okay. We will search this. I have doubt on myself. Such statements are called lemmas. Occasionally, a theorem or proof may allow us to conclude easily that other related statements are true. Occasionally, a statement or proof. Okay. Just wait. I'm getting distracted. Occasionally, a theorem or its proof may allow us to conclude easily that other related statements are also true. And these statements are called corollaries of the theorem. Okay. So corollaries are something that are derived from theorems. Okay. Now we dive into finding proofs. Before diving into that, I think I should prove if I'm correct or not. This is the first set, and this thing right below. Now what I'll do. Let's ask ChatGPT about that. My God. Am I right? Yes, sir. Mental model is mostly correct, but I tweak it slightly because there are some important distinctions in mathematics. And what are those distinctions? A statement or proposition is simply a sentence that has a definite truth value. It is either true or false. Examples, okay, fine, false. So this part of diagram is correct. Statement can be true or false. Theorem. A theorem is not just any true statement. It is true statement that has been proved from definitions, axioms, and previously proven results. Okay. So a theorem is not something that is used to define definitions of another terms. um, it's kind of like we use definitions in proofs of theorems. So maybe it's like it goes both hand in hand. Okay, this stuff is a little confusing to me. For example, okay, this is a this is true and has a proof. Fine, a true statement. A lemma is also a theorem. The difference is its purpose, not the truth. A lemma is a theorem whose primary purpose is to prove another theorem. So okay, that is the part I got correct. Think of it as a helper theorem. Fine. So mathematically, every lemma is a theorem. We simply call it lemma because it isn't considered the main destination. Corollary. This part of a diagram is mostly right. A corollary is a statement that follows almost immediately from a theorem. For example, suppose we have a theorem that every finite tree with n vertices has n minus 1 edges. So immediately its corollary can be that every tree with 10 vertices has 9 edges. Oh, okay. It's just a statement taken from the theorem. No new difficulty, no new difficult proof is required. Okay, so basically corollary is an argument. If I take a theorem, if I take a theorem or a point, basically if I use that theorem to make a statement, make an argument, that argument or statement will be called a corollary. I should write this one at least, where my understanding is going right. Corollary is definitions. This is the place I change your wording. We use statements to define terms. Not exactly. Definitions are not statements that are true or false. A definition creates meaning of term. For example, a prime number is a positive integer greater than 1 having exactly two positive divisors. This isn't something to prove. It is establishing that word prime means what the word prime means. Then we use that definition to prove statements. We follow the flow like definitions. We make axioms. Axioms are used to prove if a statement is true or false. And then if the statement is true, now this thing is classified into lemmas, theorems, or corollaries. Lemmas are basically um, lemmas are also theorem, but we call them lemmas when they are being used to prove another main theorem. Okay, when theorem becomes an NPC, we don't call it NPC. We call it lemma. Okay, that makes sense now. So a theorem which is an NPC in the world, it is a lemma. Okay, this is something I should write. If a statement is proven true, then it's a theorem. Now, if the theorem, now if the theorem is an NPC, When the theorem becomes an NPC in its world. Is that analogy good? Chat. This is the part where I got things wrong. We don't, I mean, am I really wrong here? We use statements to define terms. What is this saying me? Okay. It says me that this is wrong. We don't really use statements to define terms because definitions are not statements that are true or false. Okay. If we are going to use this to prove another statements, then isn't this a lemma? Why are you even calling it a definition? Where's that feature by which we can ask Chat GPT about? Okay, this isn't even completed. Stop between midway. Okay, so isn't that what lemma was? Definition, okay. This is not a lemma because nothing has been proved. A lemma has the form we already know A, B, C, whatever, therefore we can prove D. A definition has the form, okay, which is defined. This means something. I think there is very subtle difference. If we say, if we say thing something like this means this, so we prove that this is true. If I make a statement like this, then maybe it can become a lemma. A graph is connected if there exists a path between every pair of vertices. No proof is needed. You could have chosen a different word instead. Let's call such graphs banana graphs. Okay, the mathematics wouldn't change. Um, Definitions are conventions for a language. This requires a proof. After proving it, you might use it to prove a larger theorem. So, what's the difference between definition and axiom? A definition tells you what words mean, an axiom tells you what facts are allowed to assume. You are allowed to assume, okay. Typically, we don't assume, but whenever maths allows you to assume something, that assumption is basically an axiom. We can remember this as A for axiom, A for assumption. Okay, so see this statement precisely. We declare that players alternate turns. So, mm, can you prove this statement? I mean, it's clearly visible, right? Players alternate turns. So, you don't need to prove this clearly. It's proven by fact. Proven. This statement in itself means true. It's like the sun rises from east. You don't need to prove it. It's clearly visible. And that's an axiom. You can use it as an assumption to prove another statements. A square is a rectangle whose four sides are equal. We never know the word square, what square means. Suppose we are working with equilateral geometry through any two distinct points, exactly one line exists. This is a fact we are accepting without proof. But isn't something that you need to define points, you need to define line, and after defining all of these terms, then you can actually make this axiom true. Okay. Every square has four right angles. This is no longer assumption or definition. It follows logically from what came before. Okay. Assertion and definition, explanation. Fine. I think I have a very clear picture now. Now diving into next section, finding proofs. The only way to determine the truth or falsity of a mathematical statement is with a mathematical proof. Unfortunately, finding proofs isn't always easy. It can't be reduced to a simple set of rules or processes. During this course, you will be asked to present proofs for various statements, and don't despair at the prospect. Even though no one has a recipe for producing proofs, some helpful general strategies are available. First, carefully read the statement you want to prove. Then, do you understand all the notation? First of all, rewrite the statement in your own words. Break it down and consider each part separately. Well, that's what we do in engineering. We break down problems. Sometimes the parts of a multi-part statement are not immediately evident. One frequently occurring type of multi-part statement is of the form P if and only if Q, often written as P if Q. Okay. We break any given statement into many statements, and then we can use mathematical reasoning to actually reason if whatever statement, smaller statements are true or false, and on the basis of that, the larger statement is true or false. Sometimes the parts of a multi-part statement are not immediately evident. One frequently occurring type of multi-part statement has the form of P if and only if Q, often written as P if Q, where both P and Q are mathematical statements. This notation is shorthand for a two-part statement, which is on which the first part is P only if Q, which means if P is true, then Q is true. Uh, isn't this like implies? No, written as P double arrow. Double arrow is the second is P if Q, which means if Q is true, then P is true. I should write these things. Okay. You know, I am able to grasp by this notation if P is true, Q is true. Okay, but how is this written? P if and only if Q. This sounds like P is true if and only if Q is true. So if is with Q and not P. Do you get me? So how this statement is equivalent to if P is true, then Q is true? This notation is shorthand for two-part statements, and the first part is basically wait. Okay. Sometimes the part of multi-part statements are not immediately evident. One frequently occurring type of multi-part statement has the form P if and only if Q, often written as this. Now where both P and Q are mathematical statements, and this notation is shortened for two-part statement. The first part is P only if Q, which means if P is true, then Q is true, written as this arrow notation. The second P if Q. Okay. The first of these parts is the forward direction of the original statement, and the second is the reverse direction. We write P if and only if Q as both sides. Okay, to prove a statement of this form, you must prove each you must prove each of the two directions. Often, one of these directions is easier to prove than the other. Okay, this is not equal to this. Mm, Basically, basically this is another set. I can duplicate this. Just a minute. Fine. Another type of multi-part statement states that two sets A and B are equal. Okay, the first part states that A is subset of B, and the second part states that B is subset of A. Thus, one common way to prove that A equals to B is to prove that every member of A is also member of B, and every member of B is also member of A. Next, when you want to prove a statement is part thereof, try to get in get intuitive. A gut feeling of why it should be true. Experimenting with examples is especially helpful. Thus, if a statement says that all objects of certain type have particular property, pick a few objects of that type and observe that they actually do have the property. Pick a few objects of that type and observe. Okay, after doing so, I'm zoning out. Sorry. Okay. Experimenting with examples is especially helpful. Thus, if a statement says that all objects of certain type have a particular property, pick a few objects of that type and observe that they actually have that property. After doing so, try to find an object that fails to have that property, called a counter example. If the statement is actually true, you will not be able to find a counter example. Seeing where you run into difficulty when you attempt to find a counter example can help you understand why the statement is true. Okay, we have an example here. Suppose that you want to prove the statement for every graph G, The sum of degrees of all the nodes in G is an even number. Well, I know that this is a theorem, but for now, when we don't know anything, we consider this as a statement. Now we have to prove this as true or false. So how we are going to prove? Degrees of all nodes. The degree of this node is 1, 2, 3, 4. Okay. But okay, if I actually eliminate one node, just take two nodes, 1, 2, degree of this node will be 1, degree of this node will be 1, 2, 3. Wait, degree of this node is going to be 1, 1, 1, 3. 3, 4, 5, 6. Answer is 6. Let's say we make something like, okay, here the degree is 2, 1, 1, 4. And I'm actually not able to find a counter example. Every time an edge is added, the sum increases by 2. Every time an edge is added, the sum increases by 2. Let's say I take this. Okay, answer is 1 plus 1, 2. Now we add a new edge. Okay, this is new edge. A node will be here. Sum increases by 2. The answer was 2, and now the answer is 4. We add a new edge. Let's say like this. Now its degree is 2, 2, 2. Answer is 6. Let's say we add it like this. Answer is 1, answer is 2, answer is 2, answer is 1. 2, 2, 4, 5, 6. Answer is still 6. Okay, this is something really special. Can you begin to see why the statement is true and how to prove it? If you are still stuck to prove a statement, try something easier. Attempt to prove a special case of the statement. For example, if you're trying to prove that some property is true for every k is greater than 0, first try to prove for k equals to 1. If you succeed, try it for k equals to 2, and so on until you can understand the more general case. Okay, if a special case is hard to prove, try a different special case, or perhaps a special case of a special case of the special case. Okay, that's interesting. Finally, when you believe that you found the proof, you must write it up properly. A well-written proof is a sequence of statements wherein each one follows by simple reasoning from previous statements in the sequence. Carefully writing a proof is important, both to enable a reader to understand it and for you to be sure that it is free from errors. Um, Now there are following a few tips for producing a proof. You have to be patient. Fine. And you should be patient in all situations of life. It's not just mathematics. Come back to it. Look over some statement you want to prove. Think about it a bit. Leave it. Okay, this is something I am going to remember. Okay, to actually make my streams fruitful. Let's say if I'm not able to prove some statement in a given stream, I'll pause and come back to it in next stream. Okay, and then return a few minutes or hours later. Let the unconscious, intuitive part of your mind have chance to work. Be neat. Well, this neat word is really dark joke for Indians, you know. Be neat. Well, this is neat with an A, not with an E. So when you're building your intuition for the statement, you are trying to prove use simple, clear pictures or text. You are trying to develop your insight into the statement, and sloppiness gets in the way of insight. Furthermore, when you are so funny, it's genuinely funny. Furthermore, when you are writing a solution for another person to read, neatness will help that person understand it. Be concise. Brevity helps you express high level ideas without getting lost in details. Good mathematical notation is useful for expressing ideas concisely, but be sure to include enough of your reasoning when writing a proof so that the reader can easily understand what you are trying to say. Fine. I mean, you have to be neat, but by neatly expressing solutions, you don't mean to write every single step. You have to write in a concise way so that that's the precise meaning of brevity. Don't get lost in too much detail. Make it neat. For any two sets A and B, this is De Morgan's law. Okay, De Morgan's laws. Let's prove it. Here is proof of 0.19 as well. Okay. Sum of degrees of all nodes in G is a even number. Fine. We have to prove that if we take intersection of two sets and we take complement of the result, then we will get a result that is equivalent to you will get a result which is equivalent to this thing right here. First, is the meaning of this theorem clear? If you don't understand the meaning of symbols, union or intersection, or the overbar, complement, review the discussion on page 4. You have to understand the meaning of theorem. You have to break the problem into subproblems, things like that. Okay. To prove this theorem, we must show that these two sets, which is basically the result, okay, are equal. Uh, okay, recall that we may prove that two sets are equal by showing that every member of one set is also member of another set and vice versa. Before Looking at the following proof, please consider a few examples, then try to prove it yourself. Okay, we'll prove it ourselves. Let's just okay. We have a set A and we have a set B. From what it said me, how to prove, I think I should write an example, and in that example, I'll specify that this set A is equal to some set, let's say A, B, C, D, and then there is a set B, and it is equal to, let's say, B, D, E, F. Okay, now I know what union means. So I have broken down the statement into like this part. What is A union B? Sorry. What is A union B? And this is simply A, B, C, D, E, F. A new set. And if I take complement, then what will complement mean? This is unspecified because I haven't considered a universal set. What's a universal set? Is this coming from um let's say the universal set is um universal set, we have to represent like this, is equal to everything from A to Z. Okay, so if I'm saying this, its complement will be everything from G to Z. No. Now let's see the second counterpart statement, and that is intersection after taking in individual elements. So we do this. Based on this fact, we can break this into even more parts, you know. First we'll talk about A bar, and that will be equal to a set where you get E to Z, and B will be just the set where you have A, you have C, you have D, E, F, and then G to Z. Now let's take intersection of these sets. I just get, what do I get? I don't get A, no E, no C, but I get from G to Z. So basically this is again equal to this set. And because these two results are equal, I say the statement is true. But isn't it something like, I feel like what I've done, um, I think what I've done is basically assume the statement true and make some corollaries from it. And then just, it's so easy to prove corollaries, right? Hello. Okay. Okay, YouTube actually flagged my response. I can't, whatever I said. I said don't eat me. Uh, that message is blocked. So where was I? Let's continue with the official proof. Suppose X is an element of this set, then X is not in A union B from the definition of the complement of a set. How much lag on stream? I think there's a delay of like maybe 8 to 10 seconds from what I'm actually doing live and what is being shown to you. Oh, I'll let you carry on. Thank you, thank you, thank you. Then X is not in A union B from the definition of complement of a set. Therefore, X is not in A and X is not in B. Fine. Matlab, I see where you are going. You have just generalized. I actually took some corollaries and proved on behalf of those corollaries, but this is not the way. This is guys not the way. But is it? Is the matlab, I need someone to tell me if this is a way or not. You are thinking in the right direction, but this is not a proof in a mathematical sense. It's verification using one example. I guess right. I just use corollaries. Checking example can increase confidence, but mathematics requires proving all possible cases. The same thing happens here. So you have to generalize. Fine. Take a big red mark and put this beautiful mark here. We We can actually break the statement into many steps, but we decided not to. And that's an intuition. This book also use the word intuition. You have to use your intuition to define. You have to use your intuition to actually define what is basically the right sub problem you are going to solve. So you have to be intelligent about choosing your sub problem. You have to be intelligent for choosing your problem. So the main goal of the problem is to prove this simple statement. And despite the fact that you can break this one problem into many smaller problems, I decide, according to these books, I rather decide to break this into only two problems, and those are um, to assume just two sets. Okay, taking these parts, I say let's take an element x, and um, it is within this set in this result. And if this is in this result, okay, it must be a part of, we can write this like, if this statement is true, implies that x must belong to this part, or maybe I can use the or word here. No, or x must belong to this. So you see, I took a problem and broke it down into two problems, and now let's say this is statement P and this is statement Q, and this is like P or Q. Okay. So what now? I think I'm again going in the wrong direction. Hello chat, give me some suggestions. How should I move from this step? Suppose X is element of this, then X is not in A union B for sure. Then it is not in A and not in B. It actually used the word and the difference between this book and mine, I used the word or. So according to this again, I'm wrong right here. And that makes sense because you see, this statement would mean, let's take this in a box. This was our starting point. Let's say this counterpart, we will start by saying x belongs to this. Now x belong, because this is intersection, we will actually say belongs to this and this. Now obviously these both statements are not equating. So I'm again wrong here. Let's just see solution for once. Suppose x is an element of A union B complement. Wait, this is more. I'm wrong at this part. This is the key idea. When is an element in A union B? An element belongs to A union B when both sides are true. Okay. If this is true, okay. Well, yes, you're right. And you actually used or. And yes. Okay. We are actually moving with mathematical logics and not our stupid brain logics. Okay. Let's see this one. We said right, x belongs to, and then we say x must not belong to A union B. And then that just means, what does this mean? This means x must not be in both of them. And if x is not in both of these sets, that just means it is in the universal set. Okay, my reasoning is correct, but how do I write it in mathematical terms? How do I write it in mathematical terms? To actually write express this with mathematical notations, I can maybe write it like x belongs to A or x belongs to B. Okay. If this is true, then x must belong to A union B, but x doesn't belong to this part. So this is false. And if this is false, we negate this statement like this. Is this the right symbol? Am I using the right symbol? I think yes. Okay, now this is the or part. Okay, I should refer. I should refer to my notes, previous notes. What was the formula? We have to negate or. This is the case. Um, have I not done the negation? Okay. I think it's easy. How? Wait. Let me first. I have written P or Q basically means this part, right? Well, yes, because if I negate this right here, it will just cancel this negation, right? So negation of P or Q will actually be equal to negation of P and negation of Q. And this is exactly the De Morgan's law. Yeah, I mean, I can't use De Morgan's law to prove De Morgan's law. This will make it another contradiction. I think I can't use this theorem because this is again De Morgan's law. Mm, then why? This is interesting. Why are we even referring to this? This is exactly where De Morgan's law for logic comes in. Fine. Well, you are right, but my question is that again, my goal is to prove De Morgan's law. I can write this like this. Um, Negation of this statement that basically means X doesn't belong to A and X doesn't belong to B. Yes. And converting this to this is De Morgan's law. And if I refer to this box to prove De Morgan's law, what's the point? X is not in A and X is not in B from the definition of union of two sets. In other words, X is in A complement and X is in B complement. Fine. You are again using and. My reasoning is that why? Who gives you the right to use and? You have to go step by step. And if you go step by step, you are actually transitioning between those steps using De Morgan's law. And that's where I think you are doing some illegal stuff. You know, this part right here. You see, I should highlight this part. Um, Wait, this part right here. This and word. Who gives you the right to use this and word? Big fan. And my mathematics is so going into. Okay. So my question is that if I move with this logic, the logic that you specify here, if I move with this logic, I know it's right, but it is De Morgan's law, and we have to prove the answer depends on what is being proved. There are actually two different De Morgan laws. The De Morgan law and logic. What are you kidding me, bro? No, no. This must be legal. This must be illegal. How? Okay. It is actually saying me that I can use the De Morgan's law from set theory. It is basically saying me that I can use De Morgan's law from the theory of logics to prove the De Morgan's law in theory of in set theory. Like that statement is not digesting in my stomach. Okay. This is a statement about sets. The usable proof of set version does use the logical version, and that is not circular. Are you kidding me, bro? This is circular. This is De Morgan's law at the end. Because the logical law has already been established earlier in logic. So you mean the proof of De Morgan's law in the theory of logics is different? Okay. But what if your course hasn't proved the logical? That concern is completely valid. You would indeed be using unproved theorem to prove another theorem. Um, Guys, YouTube is actually suggesting me that audio is lower than recommended rate. What should I do? I don't know. Is my voice decent? If anyone is listening, please tell me if my voice is even decent. Okay, you would indeed be using unproved theorem to prove another theorem. In that case, your instructor is probably expecting you to prove the set version from the definitions alone. Let's do it without provoking logical De Morgan's law. By the definition of complement, X is not in U, A union B. Fine. I mean, I think the way it is trying to prove the statement now is even more complex. Okay, by definitions. By definition, A union B simply means X belongs to A union B if it belongs to at least one of AB. Fine, that's correct. Absolutely correct. So ask, if X does not belong to the union, could it belong to A? No, because then it would automatically belong to the union. Could it belong to B? Yeah. I think it's just messing with me at this point. X doesn't belong to A, X doesn't belong to B. I mean, you are just playing with words, right? Because mathematically, like by your gut feeling, yes, you are right. But mathematically speaking, can you really? Hello, hello. Mathematically speaking, I think this proof is also illegal. Also illegal, and therefore I never wrote. You never wrote this, but can you guess who I am? Well, your profile is so small, and I think this profile from so far away looks like a sloth or a cat or a dog with a hair. I don't know. Um, a hybrid of a lot of animals. I will give you hints to try, I guess. Fine. That's a good play. Here in the steps, I actually want to prove from your college. Well, in my college, there are a lot of people. I might need more hints. From a society you are in. All right, this must be namespace because I don't think Kalam is um volatile recently. Then for sure you are from literature society then. I guess wrong. Um, Still it's hard to guess. I don't know who has subscribed me from Kalam. I can guess maybe from your year, my year and Kalam. Parihar, Aditya Parihar. I think you are Aditya Parihar, but not from your branch. Okay. Um, Maybe Ujjwal from my year in Kalam. I don't know, man. I'm bad at guessing. If I were good at guessing, this subject won't be hard for me. This subject is actually hard. Nah, I know. I know I guessed wrong. Give me more hints. By the way, here, actually, I need to prove logical De Morgan's law. Anything more than this will be too easy. Well, I will tell you we don't talk much. If we don't talk much, then how can I guess, right? That's the precise point. You are pushing a great dilemma. This is a big dilemma. Maybe I can guess from Kalam, same branch. No, no one comes in my mind. Yes, yes, yes. Um, I can guess one person. Give me just a minute. I can guess Janvi. Thank you. Thanks a lot. By the way, what about my last guess? I guess Janvi. Same here. Don't talk much. The male. Okay. Deve and I also don't talk much. Oh, my message actually arrived quite late in the chat. Message also has delay. This is something new I discovered. Fine. Logical De Morgan's law. That's what we need to prove now. Yes. Thank you. Thanks a lot. Nah, nah, nah. That's not issue. Matlab, this is the thing that actually makes live streams very engaging. If you're in a live stream and nobody talks to you, then what's the point of doing live stream? I can just study off stream and be happy with it, right? But I'm actually in public studying, so this is the best part of talking to people, engaging with people. Chat also engages with the subject you're studying, and all other things in this environment. This is the precise thing that we love on YouTube. So thanks a lot. Prove me, which role are you preparing for? I'm not actually preparing for any role. This is just something I'm studying TOC because later on I want to build a compiler of my own, and kind of because I have some projects coming up. A project is an some IDE, and in that IDE I want to make a syntax parser by myself. Okay, now to make a syntax parser, you need to have a understanding of LSPs. LSPs are basically language server provider, and to make an LSP, it's kind of very similar to compiler design, you know. So, and now compiler design comes into picture, and a very big prerequisite, I say, to actually do compiler design, you must be familiar with theory of computation and all of the automata and things like that. Okay, so this is just a prerequisite. I'm studying to build something in my own personal project later on. So it's out of curiosity, out of, yes, curiosity is the right word. No role. Yeah, proving. I actually got to know there are two different forms of De Morgan's law. De Morgan's law of logical theory and De Morgan's law of set theory. And De Morgan's law of logical theory came first, and De Morgan's law of set theory came second. So we can actually use De Morgan's law of logical theory to prove De Morgan's law of set theory and not vice versa. So can you give some tips? Tips regarding what? Like precisely what? In what domain? To study TOC or to make compilers or what precisely? You were actually proving I want to become a data analyst and then transition into a data scientist role. Uh, for data analyst or scientist, I could recommend you some books. Wait, just give me a second. Um, for data analyst or scientist, right? During the analyst phase, you actually do all kinds of, what do you say, statistics and things like that. But in scientist role, you actually apply it. Um, you can get good job and good payouts with analyst role, but man, actually, scientist role is kind of less paying, I think. It's the kind of life where you actually move on to more passion side rather than money side. So if you want to transition there, you just have to study harder. It's kind of difficult subject, but I can just recommend you some books, and I will. I have some books. Just see these: data science from scratch. You can note with Python, database internals, designing data intensive web applications, fundamentals of data engineering, hands on machine learning, designing data intensive applications, and data warehouse toolkit. These all books are very, 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 very famous when it comes to data scientist, I think, and especially um, high paying job. No, I don't think data scientist is very high paying job. Matlab, you know, every 1% people in every job field is very high paying, but if you are just beginning data scientist, any company want, basically company will misinterpret you for data analyst even though you are applying for a scientist role. So at the end, this corporate sector and all of those things are kind of messed up. And first of all, it's hard to find a scientist job. Okay. I think you can guide better than. Yes, for sure. But the motive was, how can he transition, right? So to transition, I think you should study books like machine learning and from scratch, of course, data science from scratch. These are very famous books. For courses, I can't really recommend courses because I don't myself refer to courses. So how can I refer? How can I judge if a course is right or not? Um, so does that answer your question? Mostly companies don't hire freshers for data scientists. Yes, that's precise, right? If you are a fresher in data scientist and you try to apply, you will actually end up in an analyst role. I mean, yeah. Yes. Thanks a lot. I hope those books actually help you. If you want, you can DM me. I have my Telegram account. I guess you can see from my channel. Yes. Thanks. Thanks a lot. Take a hurt. By the way, Addy, do you know? I found out a very cool stuff. You will know who I am then. Well, it will be great, right? I can send you books. We can interact more. Yeah. So where was I? Okay, this is I actually found out today. Yes, what stuff? I actually found out today that I tried to prove De Morgan's law. Okay, first of all, this is the set De Morgan's law. We have to prove in set theory that A union B complement is equal to A complement intersection B complement. Fine, easy De Morgan law. I first of all understood some statements like what is theory, lemma, corollaries, things like that. And by that reasoning, I made some corollaries and just equated them and said that these two statements are true, but this is not a proof. So then I cut this whole page. Fine. Then I actually try to reason it. Let's say X belongs to A union B complement. So X belongs to A complement or X belongs to B complement, right? Because this is union at the end, but I was wrong here because I didn't include this or part in within complement, right? So if I include it within complement, this will actually transition into and. So this part wasn't right and this part was correct. But when I try to dive in more, matlab, how can I say this is equal to and? I reason again. X belongs to A union B complement. What does it mean? It won't belong to A union B, right? And this is the statement of confusion right here. We say X doesn't belong to A union B. Now, A union B is basically this, right? And because this doesn't belong to, we put a and we put not gate. Okay. Then you see an interesting thing why I have started this because this is again De Morgan's law, don't you think? De Morgan's law. And the interesting thing is that I actually arrived at De Morgan's law to prove De Morgan's law. So this is like a snake eating itself. How can I prove De Morgan's law using De Morgan's law? And this is the same stuff, right? If you ask ChatGPT is trying to prove this set theory. ChatGPT is also trying to prove this De Morgan's law using this particular statement, and I'm like, why? Why? Just why? How can you use this? This should be legal, right? But I actually found out that De Morgan's law is also classified into two different types. De Morgan's law of logics. This is De Morgan's law of logics, and another is De Morgan's law of set theory. And circular reasoning बोलते हैं इसको. Yes. No, actually not. Matlab, it's when I reasoned it, searched it, De Morgan's law of set theory came after De Morgan's law of logical theory. Okay, so logical theory was already proved. That's why we can use logical theory to prove set theory, but not vice versa. Okay, so what I'm trying to do right now is trying to prove logical theory, and this is very easy. You can use this logical you to prove this logical statement. You can actually use gates, the gates we study in computer science courses. So it's like gates, then logical De Morgan's law, and then we can prove sets De Morgan's law. um so fine. This was kind of cool stuff I got to know today. I mean, it's so basic, such basic thing, mathematical proof of De Morgan's law, and we can learn so much thing from it. But sets De Morgan's law can be proved without logical De Morgan's law too. I saw that too. In that particular proof, people are trying to prove sets theory De Morgan's law using just mathematical statements. And I think that's kind of more confusing. Uh, in a way, how do I express it? Let me just show you if I can. I think it's right here. This is trying to prove again this same part, m- but this time only using mathematical statements, reasoning definitions. That is a completely valid proof. Is that okay? Okay, ठीक है. X belongs to A and B. We are just using definitions, and just by reasoning definitions, we arrive to a conclusion. Yes, it is. All right. Okay. Something really cool. I must mark this somewhere. So these are two different forms of solutions for this particular question. I'm just saving it here. After stream, I think I can explore this because I think I don't even need to explore this. This is just solution two and solution one. Solution one is via logical statements. Fine. So I think I'm done with this theorem. It was really interesting theorem. Uh, this has also stated a lot of statements, but at the end, if we read it, it's just using logical De Morgan's law to prove this. Combinatorial story proofs. Okay, combinatorial story proofs. Let's see it. But actually, this is something always happens whenever I open OBS or stream. My keyboard manager just doesn't function till I restart it. Okay, now it works. Sorry for the delay. Combinatorial story proofs. Or proof by double counting is a way to show that two math expressions are equal. Of course, you can do this by inventing a real world counting scenario, a story, and proving both left side and right side of the equation count the exact same group of objects using two different methods. You have to invent a story, count on left side, explain why formula works, formula A counts your story, explain why formula B counts your exact same story, because both formulas count the same thing. Formula A must be equal to formula B. Okay. Classic example is okay. We are choosing R people from N people. To prove choosing R people out of N to go to a party is the same thing as choosing N minus R people to stay home. Okay, this is just saying the reverse of it. You have N friends and you want to pick R people to go on a trip. Choosing who stays home automatically decides who goes. Okay, that's right. And if we count all the people who are going to stay home, it's just total N going R. So N minus R, fine. Okay, I think I get it. Hmm. So that's your story. I get the idea of it, right? But to actually dive into the subject, I think I have this book, Concrete Mathematics, in my library. Let's see if I have. What was the name? Concrete. Yes, I have. Ebooks Mathematics, Concrete Mathematics. I remember. I remember reading this book actually. Wow. My memory is so dumb that I don't remember anything, but I remember the book name. Wow. Okay. But what did I exactly study that I just forget? Ah, yes. When I was studying DSA kind of the first time, I studied Tower of Hanoi from this book. I remember now. Recurrent Problems, Tower of Hanoi. Okay. Let's dive into this book sometime later because I'm doing book one, and book one series is a sort of computation, right? This book is really interesting. I studied this book, kind of some part of it, and this book is really interesting. Okay, that's great. Thanks, Eddie, for making me remember. After stream we'll talk on VC definitely. Right now it can be kind of maybe out of place. Too much distraction from the topic. For today, my goal was actually to complete till actually what are the types of proofs? So proof by contradiction and proof by construction. Ah, yes, for sure. Yes, yes, yes. Proof by construction and proof by contradiction. After covering these two topics, I might end the stream because in next stream, then I will actually solve exercises and some remaining theorems that might be left. Wow, study maths. Take this. Maths is love. So I think I'm done with this proof. And the next proof in the line is actually every graph G, the sum of degrees of all nodes in G is an even number. Well, we saw this proof via reasoning, right? How by reasoning? We just saw a statement which feels kind of like an axiom. Like, what's an axiom? Just say it's true, right? How can I express that? I make two nodes, okay. Now make a line between them. For every edge, this is an edge. For every edge that you add, you are just adding 2 to the degree. So what the sum of degrees now? This is the node, and in this node, the degree of this node is the degree of this node is 1. Degree of this node is 1. Answer is 2. Now I add another node. Now I add another node, and the answer must be 4 now. How can we prove that it's 4? It's 1, 2, 1. Answer is of course 4. 2 plus 1 plus 1. And via that statement, we kind of proved. So if how Eddie said, uh, proving by statements is also a valid thing to do. That just means that's also a valid proof. But how is it proving here? Every edge G is connected to nodes. Each edge contributes 1 to the degree of each node which is connected. Contributes 1 to the degree of each node which is connected. And therefore each edge contributes to the sum. Okay, it's basically proving via statements again, the same thing that I did previously. Okay, so fine. This is proved. Good stuff. So finally, we arrive at types of proof. Section 0.3 is over. Section 0.4 comes. Several types of arguments arise frequently in mathematical proofs. Here we describe a few that often occur in theory of computation. Note that a proof may contain more than one type of argument because the proof may contain within it several different subproofs, for sure. So proof by construction. Many theorems state that a particular type of object exists. Okay. One way to prove such a theorem is by demonstrating how to construct the object. And this technique is called proof by construction. What can be an example? Let's just use a proof by construction to prove following theorem. We define a graph with k regular to be k regular if every node in the graph has degree k. Okay, that can be a circular graph like this, and I actually connect all of these points. And by this definition of regular graphs, k regular graph, this must be a 3 regular graph. So again, my mind is actually uh, trying to go on that path where I did that first mistake, and I must not do this mistake again. I cannot prove this theorem via examples. I have to generalize it. So what's the statement now? For each even number n greater than 2, for each even number n greater than 2, like 4, 6, 8, 10, etc., There exists a three regular graph with n nodes. Three regular graph with n nodes. Okay, so let's say again for my brain to satisfy, I will take one example of number 4. Okay, for number 4, it is saying me that if I can actually construct four node graph, and on this four node graph, I can on this four node graph, I can make a three regular graph. So three regular graph is this. I think don't you think it's simple? I can just connect these three nodes like this. Fine. So for number 4, this statement is of course true. So how can we generalize it? Like I can prove on any case. I can show that a corollary is true, of course. But how can I prove this? Let's go to the basics. To prove a statement, you have to break it into sub problems. And if I have to break this problem into sub problems, I will actually say that there exists, I think, is a crucial term when talking about mathematical reasoning. And what does there exists mean when talking about mathematical reasoning? Let's search that thing. What does uh, what does there exists mean in mathematical reasoning? Can you give me? Okay, there exist X. I might need some formulas and stuff, some theorems for at least one item or a number. At least one item or number in a specific groups makes a given rule or statement true for sure. This book will just use statements and underlie some actual proof, but I might not be able to guess that underlying proof. Maybe I should just study examples more and then reason exercises. So, because I don't know anything at this point. Is anyone in the chat? Dear chat, do you allow me? Actually, I should decide for myself. I think I'm going to study all the examples and theorems that is given to me, and when exercises come, then I will reason and solve them. So let's see this theorem. For each given even number n greater than 2, there exists a three regular graph with n nodes. So let n be the even number greater than 2. Well, how can you let it, bro? It's already mentioned in the statement that n is a number greater than 2. I don't think you need to let it. Construct a graph G, okay, with n nodes as follows. The set of nodes of G, the set of nodes of G are all the points that are contained in V set. Fine. And the set of edges in G are, and you are taking this in union with this. Okay. I need to write this to visualize it properly. It is actually saying me, should I write the statement first? Statement is for This looks so cool. For every even number greater than 2, construct graph G. Oh my god, am I zoning out? There exists uh 3 regular graph with n nodes. Now to prove it, we take n, which is a number, which is a even number greater than 2, and then we take a graph G, which is of course a tuple of V and E, and here V is nothing but from from 0. How 0? Well, 0 is nothing, so we can include it because nothing is always everything. Okay, that's some high philosophical stuff. Let's ignore what I said, and 0, 1, all the way to, yes. Actually, if you're taking zeroth term into consideration, it's like you're taking zeroth index, right? And if you count it as a valid term, then to make n elements, you need to count till n minus 1, and that's right. Or no? No, no, yes, 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 I'm right. Um, E, how E can be equal to this? Let's imagine it step by step. It is giving me a set with two specific elements, and those two elements are I and I plus 1. And this is for all the elements, for all the elements that lie within this range, and then union that, and then union that with this set, and then union that again with this. Oh my god, this is some hard to visualize thing, I think. um this is basically I plus 1. I is going to be in between from 0 to n minus 2. This is one set, and you take union with another set, and though that another set is going to be a set with these two elements n minus, yeah, that set is unioned with, okay, this is one element, and that is again union, with a set similar to first one, but here we are taking element I and I plus n by 2, or is it I plus n by 2? Well, it looks like n by 2 and not complete, right? I plus n by 2, I think, because if it were complete, it should have, it ought to place bracket, right? For now I lies in between 0 and n by 2 minus 1. Picture the nodes of this graph written consecutively around the circumference of a circle. In that case, the edges described in the top line E, go between the adjacent pairs around the circle, and the edges described in the bottom line E go between nodes on opposite sides of circle. And this mental picture clearly shows that every node in G has degree 3. How is that mental image not imaging in my brain? Okay. Ah, okay. What is this trying to even express? Edges are always taken in tuples. So let's try to study it step by step. What's an edge? If you're confused on edges, what's an edge? Edge is a set that always takes its elements in form of tuples. For example, we can take a comma b. We might take b comma a, right? And if we take them like this, right? That means these are directed graphs: a to b, b to c, right? And things like that. So it makes sense that when then if you want to define then if you want to define this set E in form of set builder notation, then you actually have to make the element in a set. So first of all, that doubt is cleared, um, which is around this set comes in pair. This is a pair, this is a pair, and this again is a pair. Now, okay, now we need to understand how all these unions work. Let's take an example from this set. This is saying me from n to n minus 2, and n is always greater than 2. Okay, an even number. Let's take an example. Let's take an example of 6. Okay, let's take n equals to 6. N equals to 6. Now I will always be between, hanging between 0 to n minus 2, 0 to 4. Let's take I equals to 4. Okay, and if I take I equals to 4, my elements are 4 and 5. 4 comma 5 is included in this set. Fine. Fine. Okay. Now second element is, um wait, wait, pause. I But it as hasn't actually specified if I is a whole number or natural number or what. If I take all the natural numbers actually, it has just said that I is hanging between. Matlab, actually it is indeed trying to express all the like terms. And why the circle? From where the circle came? If I make a circle and its circumference, it's talking about the circumference, right? Picture the nodes of this graph. This is a graph. Nodes, okay, edges, okay, written consecutively around the circumference. Consecutively around the circumference. Let's say like these little balls floating around consecutively. Floating around consecutively. Okay, around the circumference of a circle. In that case, the edge is described on the top line of E. What do you mean by top line of E? Go between adjacent pairs around the circle. The edges are described in the bottom line of E. Go between nodes on opposite sides of circle. Nodes on opposite sides. Nodes on opposite sides. Let's say these nodes are on opposite sides of circle. And in between we have a diameter. And it's like this. Right? Okay, take that particular thing right here. We are so smart, we just changed the game to satisfy our rules, okay? So the edges described in the bottom line of E, edges described in the bottom line of E go between the nodes on opposite side of circle. Between the nodes of opposite side of circle, edges described in bottom line of E. What's E? It's Which edge are you specifying as E? Matlab, I know this is the set, right? But if I have to make it a unit circle, let's say, then I will normalize 4 and 5. What am I thinking? How did I even think normalization, man? Picture these. The edges described in the bottom line of E go between nodes on opposite sides of circle. This mental picture clearly shows that every node in G has degree 3. Every node in G has degree 3. I'm confused. Well, I mean, I'm not able to imagine what is it trying to express. Maybe the let's see. Let's see what's in the text. Because if I see that image, right, then I think I might be able to decide how the continuous line is being expressed with the set. No. And I think it is actually a single text because if I remember correctly, this specific, you're right. You, wait, sorry. You actually write these elements in form of tuple, but if you are writing it as set, I think you are trying to express it as a discrete variable. And if if that variable is actually discrete, I might go better with integers than anything else. Okay, what is this? Example 10 nodes. Edges of the form I, comma I plus 1. Okay. Why every node has degree 3? Degree 1, 2, 3, 2, 3. I think if you are trying to express edges of the, okay. Ah, edges of the form I plus n, I plus n. How can you even think something like this? Smaller example, n equals to 6. Edges of the form I plus n by 2 minus 1. N is 9. 9 by 2 minus 1. Um, I might take 4, 3. So, n equals to 10. What am I thinking, bro? N equals to 10. That's why my last number is minus 1, 9. 10 by 2 minus 1, 4. Okay, 0, comma 4. That's why. That's why. Nodes near opposite side. This diagram is actually wrong. I can easily see. Can't bring 4, 5, 5, 6. But I think I get the idea. I get the crux. And what's the crux? This is still something I'm not able to truly visualize. I made this diagram by myself. I tried to connect these two dots, but where I lost myself, where did I lost myself is the point, the line where the book says, in this case, the edges described in the top line of E. What do we even mean by top line of E? But the idea is simple. Idea is simply that there are three types of lines, and those three types of lines are being told to you by say 10. So 10 comma 0. That's what ChatGPT also made in the diagram. And should actually flag this and be, let's say n is equal to, okay, 6. I'll just take 6. Uh, Make the diagram according to 6. If I take 6 on the diagram, um, am I right? This will be 0, 1, 2, 3, 4, 5. So how does it say? For every I between 0 and n minus 2, 0 and n minus 2, this is the one, this, and this as well. All the elements that form comma I plus 1, join them as edges. Okay, for all these elements, join them as edges. So I join 0 and 1. I join 0 and 1 because they satisfy this rule. Okay, I join these. I join also these, and these. I can't bring 4 and 5 because again 5 won't be in this picture. No, 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 no. You are wrong. You are wrong. This will also be included according to this first set. And then you see second set with which we are taking the union, it's 6 comma 0. Sorry, 6 minus 1 comma 0. So 5 comma 0 and 5 comma 0 is basically 5 connect with 0, 5 and 0, 5 comma 0. So we make this, and by this we actually completed two sets. Okay, we completed this one, and we completed this one, and now coming to this we have I and I plus n by 2. Okay, between every, say this is 3 2, 0 to 2, um between 0 to 2, I comma I plus n by 2, between 0 to 2, for these three, okay, I actually make connect them with 0 plus 3, 0 comma 3, and 0 comma 3 is right here. Okay, with 1 we will just add 3 again, so this one, and with 2, this one. Okay, okay, so every, now exactly you have to see all the vertices, and now all the vertices have the degree of 3. we see we see a degree 1, 2. No, actually, man, no, look, this part is not degree. Okay, now I can I think for this circle specifically, this circle, I should make this with maybe dashed line or things like that, so that we don't confuse it with real edges. Okay, and if that's the case, yes, no, because you see, this circumference is uh, not anywhere in the rule. We have three rules, three unions, and nowhere in those unions we have circumferences specified anywhere. So basically, we have this edge, and this edge. And those three edges confirm the degree of 3 for this particular vertex. And for all the vertex, this is the case. Okay. So what it is trying to say me, there exists a 3 regular graph with n nodes, and we actually made 3 regular graph basically. Okay, you know what? My example was wrong. When I made an example, okay, things are connecting. When I made an example for k regular set, k regular, what is k regular graph? I made an example kind of like this. Uh, I said, I said for let's say, I said like for let's say, um, wait, these four are the nodes, and we can actually say something like this. And I said this is a three regular graph, and the statement is true. But this was a wrong example, because in a regular graph, every single node should have same degree. Um, and here in this theorem, it is asking us to prove every node should have 3 regular graph. Means every node's degree should be 3. And here we have degree of 3, fine. Here we have degree of 2, let's make it 3. Here we have degree of 2, let's make it 3. And fine, we have done. We are just done. And we can actually draw this on a circle. Okay. Okay. Now I understand. Huh. Guys, give me a break. I need a quick wash and break. So this is where we left off, and I actually meant we can make kind of a circle around this area. This will be an oval, to be honest. Let's just do it perfectly. You make one here, one here. The circle will go beyond page. And according to our logics, make everyone of degree 3, and it's done. And you can also construct a circle around it. Something like this. And as you see, we are actually constructing something. We are and thus it is proof by construction. And this is such an intelligent proof, man. It took me a long time, but I figured it out. There are three types of edges in this graph. One For one type, we just classified it all these edges, right? And all the diagonals are represented. Wait, first of all the edges of this polygon are defined by first two sets. Okay. And finally, all the diagonals are specified by this particular set. And thus we make complete diagram, complete construction. And we represent that construction via set theory. So amazing. We group them, and grouping is the group is specified by set theory. Yeah. So I'm I think I can ask one question, one final question before moving on from this theorem. Is that why didn't it just make why don't you just make a set for all the edges of the polygon? I mean, you you kind of classified the edges into two groups. One group made all these edges, okay, and then second group actually made this edge. So why did you classify? Can we not? Is it not possible to? Is it not possible to actually mm, make a set that can group all of these in just one go? Okay, try to make that set. And if we are not able to build that set, we will move on to proof by contradiction. Okay. Um, so we have to make a set that can represent all the edges of the polygon. We have n edges, sorry, n vertices, and to connect all the vertices together. Because there is one logic, an argument we can make is that you can actually connect all the incremental numbers. You made a group that actually classifies it like 0 to 1, है ना? 0 to 1, then 1 to 2, then 2 to 3, 3 to 4, and 4 to 5. But In the same formula, you can't represent doing plus one plus one plus one, right? I plus one, I plus one, I plus one. This is I and I plus one. Logical argument. But you can't do I and I plus one for this one, but actually you have to circular connect this to this as well. You have to connect this part as well, right? Kind of like this. So that is why I think it has made two different groups. And this is very logical. Two different groups. So fine, I think I understand this beautiful question now. Let's write one final thing. Um, these two edges of polygon diagonal of polygon. And we proved this beautiful theorem. This took me the most time, but this was the most beautiful theorem I saw in this session. Now, moving to proof by contradiction. In one common form of argument for proving a theorem, we assume that the theorem is false and then show that this assumption leads to obviously false consequence. And that's called a contradiction, of course. We use this type of reasoning frequently in everyday life, as in following example. This example is from everyday life. What is it? It is ki Jack sees Jill, who has just come from outdoors. On observing that she is completely dry, he knows that it is not raining. His proof that it is not raining is that if it were raining, Jill would be wet. The assumption that statement is false, the obviously false consequence. Therefore, it must not be raining. Let's prove the contradiction that the square root of. Okay, this is it. The example is over. Next, let's prove the contradiction that the square root of 2 is an irrational number. Okay. A number is irrational if it is a fraction m by n, where m and n are integers. Fine, that is something I for sure know. Okay. So root 2 done, we represented as a rational number. Okay, done. Then we actually say that this 2k, this k number, uh, you know what we said, this should be even. And why is that? Integer, odd number. One of them must be an odd number. Why? M and n are integers by the same integer greater than 1. Okay. Divide both by largest such integer. Okay. Doing so doesn't change the value of fraction. Now at least one of m and n must be odd number. Huh? Because if you are representing it in a simple fraction, then it must have an odd number because otherwise things would be divisible, and it would again reduce to simple fraction. So now at least one, okay, we multiply both sides of the equation by n to obtain this, and then we square it. And now because square of every number is an odd number is an odd number, but this part is being multiplied by 2. And you know what? You are actually equating odd number with an even number at this place. We know that m square is even, therefore m2 is even, as the square root of an odd number is always odd. Square of an odd number is always odd. So we can write m equals to 2k for some integer k, then substituting 2k for m, we get this. Just to prove it is, oh, hello Tushar again. Welcome back. Today I saw a very beautiful proof by construction. This was so amazing. And this is also done. Of course, even number can't be equal to odd number. We have contradicted the fact, and thus this initial condition must be wrong. There is another proof by induction. So there are actually three types of proofs mentioned here: construction, contradiction, induction. What's induction? Proof by induction is an advanced method to show all elements of an infinite that have specified property. For example, we may use a proof by induction to show that an arithmetic expression computes a desired quantity for every assignment to its variables, or that a program works correctly at all steps or for all inputs. Basically, it's a map function, and you are just applying a function to every element of a given list, right? If I imagine it in terms of programming. Um, when or that a program works correctly at all steps. To illustrate how a proof by induction works, let's take an infinite set to be the natural numbers. Let's take the infinite set to be the natural numbers, find and say that the property is called P. Our goal is to prove property P on K, because that K is basically a natural number. So this should be true for every natural number. In other words, we want to prove that P1 is true as well as P2, P3, P4, and so on. Every proof by induction consists of two parts: the basis and the induction step. Proof by construction is done. Proof by contradiction is not even gaining for attention. Then we have proof by induction. And I see one crucial step in this area: two parts, basis and the induction. To illustrate, okay, the basis and the induction step. Each part is an individual proof on its own. The basis proves that P1 is true. The induction step proves that for each element greater than for each element I greater than 1, if Pi is true, Then so is pi plus 1. Okay. When we have proven both of these parts, the desired result follows. Um, why? First, we know that P of 1 is true because the basis alone proves it. Second, we know that P of 2 is true because the induction step proves it. I think I should take a practical example for this. Once you understand the preceding paragraph, you can easily understand variations and generalizations of the same idea. For example, the basis doesn't necessarily need to start with 1. It may start with any value b. In that case, the induction proof shows that this is true for every element k. That is at least that is at least that is at least b. Induction hypothesis. Sometimes having the stronger induction hypothesis that p of j is true for every um, the basis doesn't necessarily need to start with 1, it must start with any value b. Okay. In that case, the induction proof shows that p of k is okay, fine, understand. In the induction step, the assumption that p of I is true is called the induction hypothesis. Sometimes having the stronger induction hypothesis that p of j is true for every j is less than I is useful. The induction proof still works because when we want to prove that pi plus 1 is true, we already have proved that p of j is true for every j less than I. And the format for writing down a proof by induction is follows. First of all, you write basis, prove that p of 1 is true. Whatever you write the proof, and then in induction step for each I greater than 1, assume that p of I is true and use this assumption to show that p of I plus 1 is true. Now let's prove by induction the correctness of the formula used to calculate the size of monthly payments of home mortgages. When buying a home, many people borrow some of the money needed for the purchase and repay its loan over a certain amount of years. Typically, the terms of such repayments stipulate that fixed amount of money is paid each month to cover the interest as well as part of original sum, so that total is repaid in 30 years. The formula for calculating the size of monthly payments is shrouded in mystery, but actually it's quite simple. It touches many people's lives, and you should find it interesting. We use induction to prove that this works, making it a good illustration of that technique. First, we set up the names and meanings of several variables. Let p be the principal amount of original role. Are you going to tell me the formula of compound interest or simple interest? Let I be greater than 0, be yearly interest rate. Fine. Interest rate of the loan where I is equals to 0.06 indicates 6%. Okay, fine. Let Y be monthly payment. Fine. For convenience, we use I to define another variable M. We use I to define another variable M, the monthly multiplier. It is the rate at which the loan changes each month because of the interest on it. The following standard banking practice, the monthly interest rate is 1/12 of the annual rate. So M equals to 1 plus I by 12. And interest is paid monthly. Two things happen each month. First, the amount of loan tends to increase because of the monthly multiplier. Second, the amount tends to decrease because of the monthly payment. Let this be amount of the loan outstanding after ith month. Then P0 is P, basically complete amount is the amount of the original loan. Fine. P1 is M times P minus Y because you basically multiply the multiplier in the principal amount and subtract the amount you're paying each month. Let's just say, let's just say, okay, previous month whatever amount you paid, next month how much you are going to pay? Next month you are going to pay um a principal amount of whatever you paid last month with this month's multiplier, of course subtracting whatever you paid already. Okay, that makes sense. The initial amount, the previous amount was P0 in this case of P1 and multiply and subtract whatever you paid. So this is principal amount of next month. Is the amount of loan for 1 month. P2 is the amount of loan for 2 months and so on. Now we are ready to state and prove a theorem by induction on T such T that gives the formula for the value of P. First of all, you have to take, guys, can I come to this problem and exercises all together in next session because I think my brain is not really braining after 3 hours of session. I really want to take some break, big break. So I think I'm going to end this right here. In next stream, we will walk through around proof of induction, of course, and exercises. Fine. So thank you everyone for joining. Wish me luck to continue this journey ahead. Hopefully, in next stream, I might complete this chapter 0 and we might finally dive into real TOC, regular languages, finite automata, and very cool stuffs. There will be a lot of Googling by then. So, meet you in the next stream. See ya. Bye.